where victories depend on split-second analysis, where strength can be defeated by strategy. And where animals triumph, not with firepower, but with brain power. East Africa is known as the cradle of humanity, and it's still home to an ape that thrives not just through brawn, but by using its brain. The chimpanzee, though mostly a fruit eater, is a vegetarian Dr. Jekyll disguising a carnivorous Mr. Hyde. But getting meat presents a problem. Shaped by generations of evolution to eat fruit, chimps aren't equipped with the claws, the camouflage, or the lightning speed required to hunt. So they have to rely on other qualities. Their target is a group of colobus monkeys, always alert and far more agile in the treetops. But in this story of survival, it's the smartest, not the fastest, that will win. Quietly, the chimps size up their quarry. There are plenty of youngsters, which make the easiest prey. The monkeys are in a tight corner, with few ways out. If the chimps can block the escapes, they might be able to seize a fleeing monkey. It's all a matter of strategy. The chimp screams, panic the monkeys. High up, the colobus are safe. But in the confusion, some of them break ranks. And the chimps are waiting. Slow-motion footage shows that this chimp faked towards the monkey above him, then switched direction and grabbed an unsuspecting bystander below. By using their brains, chimps make up for the limited speed and weaponry. Although they're only part-time predators, they can still outperform specialist killers. When they bother to hunt, chimps are twice as successful as lions. Intelligence is their hidden weapon. But if brains are such a winning formula, why aren't all animals armed with supercomputers? There are huge variations in brain power across the animal kingdom. The reason is simple economics. Nerve cells, which make up brains, require a colossal investment of energy. And it's not just a matter of growing them. Their running costs are staggering. Just sitting on standby, nerve cells burn up fuel, staying primed and ready for action. They require far more energy than muscle, and they never sleep. So, in a world of limited resources and ruthless competition, it doesn't pay to have surplus brain power. In fact, many creatures thrive with no brain at all. Each morning, sunlight guides these jellyfish to the surface of the water and into contact with the plankton they feed on. They don't need brains, but they do need flawless coordination. The beat of the jellyfish bell is triggered by electrical pulses, firing at over 80 kilometers an hour along specialized communication lines, the nerve network. With minimal information, jellyfish can locate plankton. But to hunt down active prey, animals need to be able to gather intelligence. Around 500 million years ago, there was a critical evolutionary leap forward, and the predators that appeared were armed with a new weapon. In its head, the land flatworm has a brain, but one composed of only a few hundred nerve cells. This tiny but sensitive computer leads it through the forest, reacting to sunlight, warmth, humidity and gravity, and to a multitude of chemical clues left by its prey. Compared to the jellyfish, the flatworm is swamped with incoming data. Its brain is there to assess this information and make the decisions that keep it on track. The flatworm is a contact killer. It oozes chemicals onto its prey, resulting in a slow, dissolving death for the earthworm. Over millions of years, such primitive struggles have developed into more elaborate contests. But the advantages of smarter brains must always be weighed against the costs. Here in outback Australia, a mud wasp is preparing her family's defences. Her egg chamber is underground. Above it, she builds an entrance tube made to an exact blueprint. At a height of 1 body length, she turns the tube through a prescribed angle, then forms a precisely shaped flange. Onto this she builds a large bell, measured to the nearest millimetre. Its size is critical to its defensive role, but so too is its texture. Though rough on the outside, the inside is polished smooth. The funnel has a specific purpose: to thwart the cuckoo wasp, an opportunist looking to plant her own eggs in other wasps' nests. The slippery funnel keeps her out. But the mud wasp is much larger than her enemy, so can climb in. But the brain behind this ingenious design is a blind computer, a machine that executes a list of instructions with no concept of what it's doing. It's incredibly economical, but a visionless machine like this has a major flaw. If it's thrown off its normal course, it's stumped. A buried tube should be easy for the wasp to fix. The hard part is understanding there's a problem in the first place. The wasp pauses briefly, but then continues on, with her routine unchanged. The result, an hour later, is a shortened funnel. Its entrance is too low to add the crucial bell. The mud wasp's brain is a miracle of precise programming, but on this occasion, her robotic inflexibility has opened the door to the enemy. Fixed programs are wired into every brain. They may be inflexible, but these routines are the cheapest way to tackle many problems. Like the mud wasp, this goose is a mindful parent. Should a precious egg roll out of the nest, she notices the problem and responds intelligently. Or so it seems. But in fact, the goosey's brain takes a shortcut and operates by a simple rule of thumb. Anything smooth and near the nest must be an egg. The goosey's powers of discrimination are actually surprisingly vague. An egg needn't be white, or even egg-shaped. Even a wooden cube can pass for an egg. But her simplified concept of an egg does make perfect sense. A more elaborate, foolproof recognition system would be a waste of energy that's better used raising more young. But for one bird, the stakes are higher. The ostrich's recognition software has had to improve. female ostriches set up a communal nest. At first, the self-appointed caretaker welcomes visitors, who each add an egg to the clutch before moving on. A large brood raised under one roof has the benefit of safety in numbers. But as the eggs steadily pile up, to 25 or more, it begins to look as if everyone is taking advantage. As her workload mounts, the caretaker gives new arrivals a frosty reception. Letting off steam seems to clear the caretaker's head and allow her to make some cool-headed calculations. A goose would be in a real flat by now, but not the ostrich. Now in egg overload, she decides to concentrate on her own. Amazingly, she can recognize each one. She carefully tucks her own eggs safely into the middle of the pile, before removing some of the surplus. Patterns of tiny surface pores vary between eggs, and this may allow the sharp-eyed ostrich to discriminate. However she does it, it's a death sentence for the evicted eggs. The better she is at picking out her own eggs, the more young she produces. Her enhanced brain power means more breeding success. But in a world of complex challenges, a refined routine is not always enough. To be truly competitive, animals must also be flexible. The power to learn may be the ultimate survival tool. Sophisticated examples exist in our own backyards, even in the brains of insects. In the last 2 weeks of its life, a honeybee graduates from hive duties and emerges for the first time into the outside world. Its mission, to bring food to the colony, seems simple enough. But a bee faces a bewildering challenge. A confusing variety of open flowers, each producing nectar for only brief periods, and at times of the day that vary from one species to the next. This makes the bee's job incredibly complicated, but with just 2 weeks to live, it has to learn fast. Amazingly, the brain of a honeybee expands with age. As it matures into a forager, it develops an additional 160,000 brain cells to help with the job ahead. Understanding the nectar production schedule requires a precise sense of time, and bees can read the sun's position to within a few degrees, equivalent to the passage of just 18 minutes. The trick then is to match the flowers to the hours. A novice forager is bound to make some mistakes, but trial and error is the essence of its strategy, and sooner or later, it gets it right. With the sweet hit of nectar, the bee's brain begins to forge a link between the smell of the flower and the time. It knows that when the two coincide, it can expect nectar. Time, measured by the sun's position, is relayed to the brain throughout the day. When the bee smells the flower, its brain takes note of the time and chemically sets itself an alarm. So the next day at the same time, it automatically knows to visit the same flower. Just one successful nectar hit is enough to connect flower and time in the bee's brain. Rapidly, the bee builds up its flower diary with allotted visiting times for each species. A quick check on the sun's position, and a bee knows precisely which flowers are open for business. The ability to connect events, to use one thing to predict another, transforms an animal from a simple robot into a flexible learning machine. But sometimes there are no simple connections to be made, and no time for trial and error. For an African elephant with a lifespan of 70 years, coping with unexpected drought is an occupational hazard. When regular water holes dry up, these thirsty animals are forced to move on to less familiar terrain. This is no place for an apprentice forager. These elephants need precise coordinates, and there's no time to lose. Elephants have a highly developed sense of smell. They can detect minute traces of water in the earth and on the breeze. But if the water's downwind, they can't detect it. To survive such a crisis, the entire herd may depend not on their noses, but on the memory of the oldest female. She alone may know where to look for water, and the key lies in a specialized part of her massive 4 to 5 kilogram brain, the hippocampus. It contains a database of spatial memories, mental maps built up over a lifetime. Before taking another step, she scans her memory and tests the journey in her head. Elephants know where they're going, even in terrain they've not visited for decades. Their epic journeys are mapped-out expeditions over ranges spanning thousands of square kilometers. Even for its size, an elephant has an unusually large brain. Drought is a fact of life, so for these thirsty giants, memory is a critical survival tool. But elephants also face another equally unpredictable challenge. They need to negotiate an ever-changing social landscape. It's the varied and complex demands of living with others that have led to the greatest advances in brain power. This is Africa's Kalahari Desert, and large or small, the brainiest creatures are the ones that live together in close-knit groups. The social meerkat has evolved a brain far bigger than you'd expect for an animal its size. The extra brain power is a huge advantage in a social environment, where there are constant opportunities to learn. Pups can pick up vital survival skills just by watching their elders. Meerkats have lots to learn about the world, and they master much of it quickly. Work out how to kill a scorpion once, and the same technique works every time. Social animals have larger brains, not just so they can learn from each other, but because they must learn to live with each other. Social awareness relies on recognizing and remembering individuals. But social harmony is not an idle luxury. Meerkats depend on close teamwork for their survival. In family groups like this, helping others comes naturally. But in other groups, where strangers mix, animals need to adopt a more calculating attitude. These bats are vampires. The bats numb their victims with a strong anesthetic contained in their saliva, then slit the skin with their scalpel-sharp teeth. The victim feels nothing, so the bat can feed freely. As it eats, the bat's stomach stretches to accommodate huge quantities. It can drink enough blood to last 2 days. But this type of hunting is not as easy as it looks. It's a high-risk way to make a living and requires more than simple stealth and sharp teeth. If it fails to find food, a vampire bat can quickly starve. After 2 nights in a row without food, this bat's life is on the line. Its only hope now is to find another bat prepared to share some of its spare blood. The starving vampire begs for food. And it's rejected. It needs to find a friend, a grooming partner. If it's to survive, it has to remember which of these roost mates it has helped previously. At last, it finds a partner, a bat who owes it a favour. The starving bat inserts its tongue into the other's mouth and drinks regurgitated blood. This life-saving act will be remembered by donor and recipient alike. Sharing tendencies like this make a precarious lifestyle a bit more secure, but they rely on vampires having the brains to keep score. Only by counting favours do the bats know who to turn to in a crisis and who to ignore. The blood bonds among vampires are reminiscent of more intricate social arrangements, of animals more closely related to us. These are macaque monkeys in the forests of Sri Lanka. Coalitions dominate the macaque's daily life. Even the infants cultivate friends and soon learn who they can count on. These creatures network obsessively. This is no place for the socially inept. Macaque society can be violent, and scarred faces are proof of savage infighting. When trouble erupts, it helps to have friends. Life in this society would be intolerable if it weren't for allies. Monkeys are social animals, but they are also competitive. And not just in physical ways. Theirs is a battle of wits, fought as much with brains as it is with muscle. Living together is a constant balancing act, weighing the urge to compete against the need to cooperate. Alliances hold the violent macaque society together. But the dangers of conflict have driven another monkey to develop a remarkable anti-war strategy. These are geladas in the highlands of Ethiopia. Like macaques, geladas form close bonds and rely on well-maintained social networks. But this huge gathering is not a single troop. It's a collection of smaller family groups, each one headed by a single dominant male. Each has several females and their young under his protection. Their daily business is much like the macaques. But these monkeys are far less inclined to give each other a serious mauling. Life here is no less competitive. On the contrary, many family groups are drawn to the same prime grazing grounds and have to compete for limited food and space, which can lead to dangerous tensions. But amidst this chorus of noise, brewing fights are somehow quickly diffused. Against all expectations, an unlikely harmony prevails in gelada herds. And it may be because these chattering monkeys have developed an unusual talent. This volume of noise is unique among monkeys. It ebbs and flows continuously, like one gigantic conversation. Gentle and soothing, this strange hubbub helps keep the lid on simmering tensions, and most of the time, they all stay relaxed. But the social skills of monkeys have been eclipsed by other species. Under the waves, arrival intelligence has been developing for 60 million years. Dolphins are also intensely social animals and tireless communicators, and they too live in societies ruled by friendship and alliance. But scientific evidence is now pointing to something new. The bottlenose dolphin is one of the only creatures on Earth other than man that can see things from someone else's perspective. It can actually make an imaginative leap into the mind of another being. Picturing the world as another sees it allows the dolphin to explore new possibilities. And armed with this kind of insight, the actions and intentions of others become easier to read. Feelings, such as a calf's need for reassurance, can perhaps be imagined. And so too can another's lack of knowledge and need for example. Such leaps of imagination are complex computations, but a dolphin can't compete without them. As far as we know, only one other group of animals has ever developed this ability. The power to contemplate the minds of others is a weapon also evolved by apes. Anticipating rivals is a crucial skill. Those who can read others well have a distinct and powerful advantage. But to be able to fathom the minds of others, you must have some level of understanding of your own thoughts and motives. You need some form of conscious awareness. Grooming is at the heart of chimpanzee social life. It's a pleasurable activity that can cement lifelong friendships and secure But for these scheming creatures, there are other ways to conduct politics. In the hands of a chimp, a prize piece of meat is more than just a meal. It can be a gift that will buy future favors or seal a strategic partnership. This kind of conscious manipulation is commonplace among humans. And just as in human society, chimps need more than simple brute strength to stay at the top. When chimps bid for power, alliances make all the difference. It's political strength that really counts. Fights within the group are rarely lethal, but it's a different story when chimps run across outsiders. Violence between groups may have driven the most extraordinary advance in brain power. Throughout our own evolution, we have, like chimps, clashed with rival groups. One thing that made us develop differently was our invention of weapons. They made human conflict much more dangerous. The survivors were those who could live together in big groups. But the bigger the group, the greater the skills needed to hold it together. In other primates, physical grooming is vital for bonding. In humans, it's been replaced by a much more efficient mechanism: conversation. Human speech is a masterpiece of biological evolution. Yet above all else, we use it for small talk, to forge and renew social bonds. Grooming has given way to gossip. Our chit-chat, though, is far from idle. It's a critical tool in the ultimate competition: courtship.